Afternoon, my name is Luke and I just wanted to run you through my 4-part series on how to use Bayesian inference and optimization, BIOMEC, which stands for Bayesian inference and optimization for the Monash electrochemical simulator, BIOMEC. And this can be found on GitHub, and it can be downloaded and installed for any computer device. It runs in a Singularity container, but it should be able to run on any Ubuntu based system, either on a supercomputer or on just any free install Ubuntu, which you can very easily install. Well, not easily, but like you can get it and install it on your computers. What it is it's basically just something that's designed for Bayesian inference, which is basically just a way of identifying parameter values and uncertainty when comparing experimental data to simulated data. The more simple optimization, which is just a least squares fitting in general sense. For the Monash electrochemical simulator, or MECSim, which was designed and written by a colleague of mine, Gareth Kennedy, and that can all be found on his website. And a Python plugin for the use is found in the GitHub repo for this thing. And I will put up a GitHub repo probably somewhere like there in the link, and you can follow that as you want. So primarily, this 4-part series will consist of 4 parts. 1, 2, 3, 4. And basically what this will be is it'll be 1, what BIOMEC is and basic uses of MECSim. And basic uses of MECSim. The second thing will be actual using BIOMEC and optimization. The optimization algorithm used for BIOMEC, which is the CMAS algorithm by Hansen, I believe, and it is the covalent matrix adaptation evolution strategy, and I'll explain that more in part 2. Part 3 will be general Bayesian inference. And part 4 will just be how do we use all of these things together, with probably an example on experimental data. Now, if you're watching this, I assume you either have a basic understanding of voltammetry or electrochemical processes, but what BIOMEC is and what MECSim is basically a simulator for simulating dynamic voltammetry experiments, fundamentally designed for Fourier transform AC voltammetry. However, it should also work for DC voltammetry, but the main focus has been, generally always has been, the use for FTACV, due to it just being more accurate and more of a focus for our research group. But what MECSim is it's basically a PDE solver or a finite difference solver. for Fourier transformed AC voltammetry experiments, assuming a free electrode system and linear diffusion from the working electrode surface. It generally just simulates the line to be quick, and it will do normally between 2 to the power of 17 data points in the PDEs, assuming fixed diffusion in solution and either Butler-Volmer or Marcus-Hush on the surface of a working electrode here. That's pretty much that for that. So probably MECSim itself is basically just a EXE available for Ubuntu, Windows, and I believe a Mac computer, which runs an EXE, where this is a Fortran 90s bit of code, which takes the input file master and outputs to a text file MECSim output/pot. You can vary a range of parameters in this, such as temperature, uncompensated resistance, your starting potential, your reversing potential, your scan speed, your cycles, a whole range of stuff. And then you have your more mass-intensive ones that we generally do not care much for. The biggest, most important value is this one here, which is the number of time points that we simulate it for. Now, partial differential equations themselves are generally only as accurate as the number of space points that you take. So if you're simulating as a point, with this being the working electrode and this being the bulk solution concentration of a region of bulk solution, you will simulate X number of spatial points in this region, generally at different positions in time or an expanding grid for accuracy. But you'll also, as this is a PDE for diffusion, it's also time dependent, and you will simulate X number of time points. Now, the parameter we highlighted previously is the number of time points we simulate, with this being n to the power 2 to the power of n time points, or split tn. Now, this is what we usually modify to get the accuracy. For most of my experiments, which are around 13 to 15 seconds long, we use probably around 16 to 17 time points. But it's important to remember, 2 to the power of either 16 or 17. But it's important to remember that in modeling all these time points, that if you decrease the number of time points, you're going to get less accuracy, but the amount of time required to do all the calculations is going to halve. And it's very much a balancing act of, do we need the added accuracy? And if so, can we reduce? If not, can we reduce it? And we generally check this. For DC, you would just generally simulate a DC voltammogram, something like that. For something like this, you probably need 2 to the power of 14, 2 to the power of 15, but you would simulate this and then decrease the accuracy until you stop getting the exact same result. Because obviously you'll end up getting a plot where it looks like Y is the accuracy and X is 2 to the power of n. You'll end up getting something that looks like that, where this is just 100% accurate. You want to get too close to this line, but not waste too much computational time in S. For FTA-CV, you'll end up probably looking at the highest harmonic you'll get in the information, and if it's remaining constant, that probably means that it's a good sample size. If you use weird values of DT, you're just going to get really weird parameter values for you to calculate. Moving back to the output here, we've moved into that, and then we have all these other things of normal stuff. Other things of interest would be your Marcus Butler-Volmer, which defines the electron transfer at the working electrode. You also have your planar surface area of your electrode, number of AC sources. If you want DC, change this to 0. Change either amplitude or frequency to 0. Your number of initial concentration of your species, so your number of species and the number of the initial concentration, the diffusion coefficient of that, and whether or not the surface is defined. Your capacitance parameters in farads per centimeter squared, which is important. And also generally just these will be your reactions of your system, where the first number specifies the type of reaction that's going on, either electron transfer, first order chemical reaction, or second order, as well as your reaction happening at the electrode surface, gathered by either a -1 or a 1. For your number of species, here we have 2, but this would easily become 3 if you increase the number of species to 3. Your chemical reaction forward and backwards, your formal potential, your K0, and your alpha. And generally what happens is you would simulate this and you would get an output. So here we have some experimental data used for FTA-CV. The important thing with these methods is you don't always require triplicate data, but for the more harmonic-based methods, you will need triplicate data for the Bayesian to use for harmonics. You can always use the total current methods for Bayesian inference and optimization. And all the optimizations, there is a whole range of functions available, such as using the current of a harmonics to analyze it. When experimentally fitting it as well, you're probably going to need to fit the double layer capacitance or the capacitance that happens outside of a Faradaic region for analysis. In this program we use, there's a lot of capacitance fitting software, but anything really works as long as it's fit to a polynomial or a constant value simulations. And if this isn't available to you, you can fit it as a constant quite easily in any of the optimization algorithms, as long as you have a reasonable starting point. So this is one of the harmonics looks like. Here you have the first harmonic here, the background capacitance in this region here. Now when we are fitting it to the background capacitance, we end up just picking, say, a region here, 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 here, and here, and then we fit to the background like so. This isn't the nicest of backgrounds, but it should be fair enough for what we're going to use it for. When I'm choosing triplicate data, I end up looking at the fourth harmonic, mainly because it's far enough away from the capacitance, so that isn't affecting the harmonics, and it's got enough of a Faradaic signal to be not that affected via just random stuff that can happen between experiments, such as distance between the working and reference, or working and working reference and working and counter electrode. You can fit that like so. Now I'm just going to quickly load up 5 triplicate experiments. I recommend at least 3, preferably 5, ideally 10, but it depends a lot on your experiment conditions. If your experiment's really difficult to get, it's going to be quite hard to get 10 triplicates. If you have to do 10 experiments to get one single bit of data, getting 10 of those is going to be quite difficult, so something more like 3 to 5 is probably appropriate there. The main important thing is you want to take the largest harmonic signal you can as well, mainly because the largest one is going to be your strongest signal with the cleanest electrode and the lowest resistance, which is generally what you're going to want data, or more abstractly, it's the ideal case. Okay, so I've just loaded up 5 triplicate experiments, and this is what I would like to call probably on the higher end of what you're going to get for triplicate experiments. We look at the peak currents at these values here and this value here, and generally, as long as they're reasonably similar, it's good data for what it wants. These harmonics information here for the forward process and here for the backward process also looks very symmetrical, which is also very good, and very defined. This is, again, the fourth harmonic, so the midpoint potential here is where your reversible potential is also occurring for your reaction. Other points of interest may also be here, where here you can see a very small amount of ringing, which is due to how we extract the harmonics. In BIOMEC, we have one other at the moment, function that we can use to extract the harmonic information in a better way to extract the Faradaic component and current component and remove the noise that is a result of the windowing function. With that being a convolutional Gauss function published by another colleague of mine. Apply this. Generally, the window ranges are the same, except you'll have an STD function or a standard deviation of your Gaussian function convoluted with a windowed function. Be explained there. Yep. It should also be noted that with this data, as we're looking at triplicate experiments, we should take the most middleist data when making like single point comparisons, so plotting. Because what BIOMEC will do is it will take, if presented with multiple sets of data, it will take all of them, calculate all the harmonics for every single one of them, and then calculate a mean for all of them. So that would be something more akin to the blue one here. Quickly fit that with MECSim and show you the process of doing that. For ease, I'm probably just going to use the first harmonic as well with some data I've fit to the capacitance as well. Okay. As well as those stated, the ringing can be seen to be a lot worse here for experimental data, and I again strongly advise on using the convolutional Gaussian function to just absolutely strip down this background. I believe this will still be here, but you can just truncate that using time series and just set it to 0 in essence. It will make your life easier, and the computer will have a lot better time focusing in on the important section here. So here we can see with the change of resistance in K0, we have a slightly better fit in the forward process, a better fit, but still not the best in the backwards process. Now we could sit here and we could change the resistance for K0, we could change them up and down. The fusion as well could be something we could fiddle around with within reason. We could change a lot of parameters. For an E mechanism, around 6 or 5, very easily do that. The formal potential is also a bit wrong in this system. We can fix that. But we could sit here for ages and do this, and then we'd have to go up into the higher harmonics, do it for all those as well. But that's very time consuming and not the best use of my time, where I could send this off to a computer, have it run the analysis on the average of all the experiments, or all the experiments overall, come back after I get a coffee, and have the parameters the best fit. The important thing to know is we have a MECSim file, which gives us a good parameter guess. We also have a good approximate estimate of a thing. In my next video tutorial, I'll show you how to use the general global optimization and probably explain to you some of the more basic optimization functions we use, the more common ones specifically being the harmonic percentage, Bayesian harmonic percentage method, as well as the experimental noise, as well as the total current difference squared method is probably the most exceptionally easy. Anyway, hope you enjoy it, and I will see you on the next video.